Hello and welcome to our Senior Design Showcase presentation for understanding thermal and fluid transients in semiconductor device structures. This project was sponsored by Micron Technology, a leading producer in semiconductor devices, and our team includes me, Cody King, and Christian Fackrell, Tyler Hamer, and Riley Winters. So our problem is the lateral size limit has been reached for transistor size, leaving 3D scaling the only viable option. And production of 3D devices is needed to increase efficiency and memory capacity in electronics. However, the complex designs have a higher cost, time to produce, and increased risk for defects. One way we can approach this is to use a computational model to efficiently predict chemical vapor deposition efficacy in varying conditions. These models can be used to inform decisions in the research and development that can streamline processes and reduce defects. And some background on CVD. Film growth in CVD is a result of a series of complex gaseous reactions between precursors, precursor fragments, and the substrate. Film growth begins when precursor fragments either nucleate, attach to ionic steps, or favor uniform coating. Film uniformity becomes an issue as the aspect ratio increases. This is an example of thermal CVD of molybdenum disulfide. The walls and edges of the trench are more difficult to cover, resulting in areas with thicker and thinner coverage. And some background on atomic layer deposition. It's a form of CVD, but it utilizes multiple cycles instead of one continuous reaction. The reactions are self-limiting and irreversible with a very high delta G. ALD is also more precise and time-consuming than CVD. Some of the challenges with both of these as the aspect ratio gets higher is film uniformity and thermal fluctuations. So our technical approach is we started with in-depth literature reviews and COMSOL tutorials. Then we created a computational model using the transport of diluted species and laminar flow modules to show the behavior of trimethylaluminum and ozone deposition on a silicon substrate in an ALD chamber. We were able to simulate a reaction chamber using finite element analysis and fluid transport modeling to illustrate the movement of gas molecules towards a wafer surface. As shown in the animation, the surface achieves saturation in under half a second. In summary, the motivation for this project is Moore's Law to improve the efficiency of 3D memory devices. The program COMSOL Multiphysics was used to model the ALD of trimethylaluminum and ozone. The model can be expanded for different materials, environments, or geometries, saving time and money for the research and development process. And we'd like to acknowledge our sponsors from Micron, Dr. Economy, Dr. Hughes, and Jim Hoffman. We'd also like to acknowledge our BSU faculty, Dr. Ackler, Dr. Millett, and Francisco Castellan. Thank you for listening, and please join us if you have any questions. Thank you.